I have only one aim today, that you enjoy yourselves, right? So please relax and watch this. And second thing is, if you learn a little bit more about artificial intelligence, following from Professor Her talk, you'll be great. So I'm going to show you how, when prediction is something that is very important to your customers. Basically, competitive edge comes from prediction. Predicting whether this bridge we design will hold, predicting whether the jet engine is reliable, predicting whether in Formula One, when you do a pit stop, it is the right timing, right? These are the things that will be important to your customers. And a lot of times, all these years, we have used science to help with prediction, as you have seen with Professor Her talk, right? The key question is, as the professor also said, can data be used for prediction? Not just science, right? I use the word history, right? The historical data. So this is the subject of my talk today. Let's just talk about prediction in general today without history. Okay. This is the LZR swimsuit. They got the top swimmers in the world into a flowing pool. And what they do is they observe these micro-turbulences that are generated by the vibration on the skin. Then they scan the top swimmers in the world, put them through this fluid dynamic simulation to try and predict what's the best shape of a human and the best surface for a human for the swimsuit. They worked with NASA on the material and then came up with the LZR swimsuit. Silver areas are hard, that shapes the body. Black areas are areas where it is sharp light. Apparently the simulation tells them that's the best one. And this is Michael Phelps. He really swims like a fish, right? 23 of the 25 world records at the Beijing Olympics were broken with this swimsuit. There were people who say that this is technological doping. Yeah, and in fact, the Olympic Committee said all records hold, right? Now, this is the good one. Even Nike-sponsored swimmers went to Nike and said, please let me wear Speedo. It was that good, yeah? And in fact, I can show you an example of the world record team, the 4x100 freestyle, the record at the Beijing Olympics that's still standing today. It's going to be very hard to beat after 10 years even. 2 of them are Nike-sponsored swimmers, and 2 of them are Speedo swimmers, but they're wearing the same LZR swimsuit. The first person to raise their hand and spot the difference, maybe get a prize from Ralph, okay? Right, okay. Yes. You will notice these 2, 1, 2 are the Speedo-sponsored swimmers, right? These 2, no logo, with a Nike hat, are the Nike-sponsored swimmers, right? So Nike said, okay, you wear Speedo, but scratch off the logo, right? But Nike was patriotic here. So this goes to show how computer simulation, right, can help prediction and design things that are way out there. This is an example from the internet, YouTube. Yes, it is essentially a MRI scan over time of a human heart and composed into a movie. There are many people who say, I need to watch this every night before I sleep. Yeah? Right? It calms me down. This is the real heart. There is a Living Heart project that's trying to build a true digital heart. Yeah, we are part of that team, and the idea is to create a faithful reproduction of the heart, not just mechanically, muscle, not just fluid-wise, blood, but also electrically. Heart works electrically, and combine the 3 to represent a heart as faithfully as possible. One of the early application of building this digital heart, the digital twin, is pacemaker insertion. Apparently the wire breaks, right? There was a 2-year-old girl who had to have a pacemaker inserted, and by the time she was 20 years old, the wire broke 3 times, and it had to be replaced. So trying to figure out the best way to insert the wire and the type of wire is important, and they're using this digital heart to try things. Don't try it on a human, right? Yeah. This is a Formula One pit stop. How long does it take us to go to a shop to replace the 4 tires in our cars, roughly? Well, 1 hour, half an hour. Want to guess how long this one will take? Let's have a look, yeah? This is a world record. Yeah, it comes in. Tires are out. Tires are in. And it goes. 1.92 seconds. The Williams team holds the record. It's currently 2 years. You can see again, out, in. Yeah. One more shot here from another camera. There we go. You notice this guy is really proud of himself. Yeah? Right. Yeah. Now, the pit stop's 2 seconds. It's very little time, but it's a lot of time in Formula One racing, right? So they have to design strategy very, very carefully where and when to do the pit stop and why, right? Because pit stops allows you to have fresher tires and overtake, but then you waste the 2 seconds, even though it's short. So a lot of Monte Carlo simulation. They run a lot of these simulation on computer to try these 10,000 different variations of pit stops, to see which one would be the best. Yeah. This is Tokyo, 10 kilometer by 10 kilometer, and they're very keen about knowing if there was a particulate released here, how will it flow through the city? So they run these simulations here of the lines are the airflows. So from there, they run these different scenarios for the city planners to see how they can change the structure of the city to mitigate certain things. Yeah, right. So in order to do that, you have to run these predictive models to see how things would go if this scenario happens. Yeah. Yeah. So all this are related to the top-down approach, as Professor Hertog's mentioned earlier, the science approach. And that is, you live by laws and rules. You hope that there is a law that guides the prediction, Newton's laws, scientific laws, and so on, and then write the laws out in equation. Then you send in the current condition and hope the law will predict for you the future. That's how I lived for 30 years. Yeah, just relying on this. Now, if there are no laws, you can write rules. You call an expert in and ask the expert questions and try to write the expert's knowledge, that's why it's called a knowledge-based system, into an set of if statements and rules and put it in there and hope it can be a prediction also. Right? So there are 2 ways. If there are laws that you can use, or if there are experts you can call in to create a knowledge base. Yeah. Let's have a look at some examples. I'll give you examples in science and also examples in the stock market, which I've, with HPE, spent quite a bit of time recently. This is Earth and this is Mars. And in order to fly to Mars, you don't fly to where the Mars is, no. You first have to predict where Mars will be and then fly there, right? And this is how it works, yeah. There we go. And that's exactly how NASA plans it, right? Yeah. This is all based on, interestingly, Newton's equations still hold. For all planets in our solar system, except Mercury. It doesn't work for Mercury. And that's what Professor Hertog's equation, you need Einstein's equation for Mercury. Interestingly, Newton became very famous when, in the early days, they observed the orbit of Uranus, and it was a bit odd. And based on Newton's equation, it says there must be another planet behind it, and they discovered Neptune. And that's why Newton became very famous at that time, for the discovery of Neptune, his equations. Then they turned their telescope to Mercury. Oh, the Mercury orbit is also very odd. So therefore, there must be another planet behind Mercury, and they call it Vulcan. And for years, they looked for it. It wasn't there, until Einstein came along and explained the orbit, odd orbit of Mercury. So it works for all planets, and in fact, can still go to Mars with Newton's equations. And you put that in, and you do a prediction. Yeah. We heard about drones being important to Intel. We work with NASA to build quiet drones. Yeah. Yes. A lot of people want to build drones that have long battery power, carry heavy load. NASA wants to build quiet drones. I don't like quiet drones. When they come with cameras, I want to know they are coming. Yeah. But areas in red are likely high-pressure areas with that will create noise. Now, don't worry about this next equation, but for an engineer, this is the most important equation for engineers you work with. It's called the Navier-Stokes equation. Don't worry about it. It is such a beautiful equation that can predict turbulence, do it for air, do it for liquid, can handle subsonic, supersonic. It's such a beautiful equation that most of the engineers you work with in engineering will be working with these equations for prediction. But like all beautiful things, there's a slight mystery to it. Yeah? An engineer knows how to avoid that mystery. If you can solve that mystery, the Millennium Prize is $1 million. Right? So there is a girl, if you watch the movie Gifted, yes, it is a movie about a little girl, 8-year-old, who grew up almost solving this problem. Yeah. Do watch it, it's interesting. Again, you can see, based on the set of laws, in this case, they call them laws of thermodynamics. Yeah? So laws and rules. Do these things exist in the stock market? In fact, they do. Right? That's the reason why you hear some parts of the financial market in Wall Street hire NASA scientists. What for? For a product called derivatives. I didn't know this until I started working for HPE and meeting the Wall Street people. All the cash in the world, 20 trillion. All the stocks in the world, 100 trillion. All the debt and bonds and treasuries in the world, 200 trillion. You know what's the biggest of all? 500 trillion. Derivatives and option. Right? It is essentially a bet on everything else. And this is what caused the 2008 crisis anyway. Yeah? Right? Derivatives, bets. Then how do you price a bet? Right? In a racehorse environment, you had punters giving you odds. But how do you price a bet? In fact, they use the Black-Scholes equation. This one won the Nobel Prize in economics. Right? So even in the financial market, they use scientific rules, right, and laws to help guide them. Scholes and Merton were awarded the prize. Black passed away, right? But Merton was very nice. Yeah, he said, call the equation Black-Scholes. Yeah, and when you go to the financial market, they only know about Black-Scholes. Yeah. So I like this about the scientists. Yeah. Good. Right, so you can see, use this, put it in there, put the current price, it'll predict you the future price. Is there a rule that they apply? Yes, in the stock market, they have automatic trading. What they do is write an if statement in the rule, since there are no law to try and predict the stock price, buy or sell. They say, if the short-term 50-day moving average cuts over the long-term 200-day moving average, don't come and talk to me, computer, just go ahead and buy. Yeah. And if it goes the other way, don't talk to me, just go ahead and sell. So it would be based on a knowledge-based system because they have spoken to a stockbroker that have experience with this stock, and it works out that this is always true. So you write it in the rule. Then comes a new way. Right? This is the one I want you all to focus on. For 30 years, I lived this way. And then recently, when I started to talk to the Wall Street people, I realized that they have found a new way. Not to replace that, but to augment it. This way says, don't tell me about rules. Don't tell me about physics. Don't tell me, of course, you still have to study your sciences, right? But don't tell me about it. Just show me your history. And just based on your history, I'm going to use it to predict your future. That's essentially what machine learning is. At least one narrow field of machine learning called deep learning. That's what it is. No science, no physics, no rules, no experts. Just show me your history, and I consume your history, and I'll use your history to predict your future. If you forget everything else, right, about machine learning that achieves intelligence, it is this. Right? This is what it essentially does. So when I was approached with this, I said, I better do it myself. All right? So I went back, got my engineer to do this. I had an engineer that was free for a week. I said, okay, predict for me whether it will rain at San Francisco airport tomorrow. And by the way, no physics, no science, no talking to meteorologists. Just take the 40 years of daily weather reports of San Francisco airport. Just take it in, right? And each weather report gives you all these 10 things, right? And then 40 years means we have 15,000 days, right? So what the engineer did was just feed the very first day into a machine learning algorithm that you can actually pick off the internet, right? Machine learning algorithm. And then before you feed it in, you assign everything of equal importance. It is not true, but just start with everything in equal importance. The key is to find out which one more important than the other. But you have 15,000 tries, right? 15,000 days. Take the very earliest day, feed it in, guess. Never mind, just randomly guess. Rain. Then you check the next day, oh, it's no rain. Wrong, right? And what you do is just go in there, the machine will, algorithm will just adjust the weights for you. Sometimes even randomly, some higher, some lower, never mind. Why? You have 15,000 tries. Second day, third day, fourth day. After 15,000 days, that was the ranking it got. These are called weights. Google call them tensors, and that's essentially what you do in machine learning. You essentially guess until you are good enough, right? And I asked my engineer, what is the prediction capability of these weights? He put it on his mobile phone with these percentages, takes today's weather in, feed it in, it predicts whether it rains tomorrow at San Francisco Airport, 82% accurate. Meteorologists, 95%. Not as accurate as the science-based method, but very, very fast. It just feeds it in and it gets the answer. While the meteorologists have to run through computer simulation on a supercomputer for 3 hours to run the weather prediction. Yeah. And this is basically what I've learned, and I hope you absorb a little of this. Machine learning that achieves artificial intelligence is not complicated. All you're trying to do in that approach of machine learning is to try and figure out the weightage or the relative importance of the things that matter to your prediction. And you achieve that relative importance weightage only by looking at history, no science. This is a very important point, yeah? If you absorb that, I think you are already good for AI, yeah? At least 80% there, right? So now there are two ways to live. You can live the scientific way, you can live the historical way. But one cannot do without the other now, right? This way gives you the precise answers that people live by. This way, as Professor Hertog say, is opaque. It will give you a prediction, but it cannot tell you why. Oh, somehow, over 2 million tries looking at my history, this is how I arrived at, yeah, right? There are methods that people use to predict drugs for disease here, and you can't just take the drug and go to the FDA, please approve this drug. And the FDA asks you why? Oh, I don't know, right? You can't say that, right? You still have to go back to your science, right? Prove that the prediction is correct, and then present to the FDA the results from here, not here. Right? The two things live together. This is very fast, but less accurate. This is the gold standard, but slower. There are people combining the two. Yeah. The other great thing about this in the stock market and finance market is the laws of Black-Scholes equation did not predict human irrationality. Right? When people go a bit irrational in the stock market, the laws don't predict them. However, this one, the history has human irrationality in the history. You see? So you can see the pros and cons between the two. So I sum up this entire talk. Don't worry about all the names too much, but I just wanted to put it all down on one piece of paper, and you all can take a picture so that you can use it as a reference. So really, there are two methods, right? The laws-based and the history-based. And people call it machine learning. Machine learns to be artificially intelligent. Yeah? In there, you're trying to predict a point. That is, what is the stock price going to be tomorrow? A point, right? Here, don't worry about the name. It's essentially what statisticians say regression. Meaning, give me all your history of points. I'm going to put it out on a piece of paper that is all over scattered. And then I'm going to try very hard to draw one straight line across all the points that will satisfy everybody somewhat. And then I extend the point further out to predict tomorrow. Right? So that's regression. The category one is the exciting one. If all your pictures to recognize cats, right, are labeled, which makes it very easy for the machine to learn, it's called supervised learning. And what the machine is doing is classifying all the cat pictures together, all the human pictures together, because they are all labeled. If you want to make it really tough, don't label it. This is frontier. All the machine can do is cluster. It doesn't know what they are. They just cluster similar pictures together, right? And Google did this with 10 million images and put it through their data center for 3 weeks, and out came 2 big clusters in unsupervised learning without labels. When they look at them, the first big cluster were cats. The second biggest cluster, humans, right? So cats before humans. It turns out like that for YouTube pictures. Yeah. And of course, reinforcement learning is another new frontier where no history at all. You just get 2 machines, just given rules and reward, play until it become good. Yeah. This one is a new method, yeah. And then finally, don't worry about all the different methods to do these classification, clustering, and regression. Don't worry about the names. The most popular is deep learning. You will hear deep learning. Deep learning is one way to do neural network. And neural network is one method of machine learning. And the machine learns to be intelligent. But there are many, many other ways to do this. Yeah. This is the most popular one because the Googles of the world have invested billions of dollars in here. So people are focusing here. Right? It doesn't mean the rest are not useful. They are. We've used them different ways before. So this is that slide that if you have it with you, will give you a good reference. Whenever you hear a term, you know, oh, okay, where do they sit? Right? Mm-hmm. So how do we then measure how good these have become in the world? 3 ways. The world have decided, because of investments, 3 ways to measure how good machine has become relative to humans. 1, images. 2, language. And 3, games. So let's look at images. There is a benchmark. 14 million images are put together by a team to form a challenge to see how good machines are relative to humans. In the year 2010, machines using not deep learning, but image processing methods, the rules-based method, were 25% error, while brain, humans, 5% error. Not as good as human. Why? The image processing method, the old method, were very good at recognizing paintbrushes here, not good here. It got confused when it came to the right side. Very good at sunflowers here, not good here. It got confused on the right side. So then came deep learning, where they started to label these images. There is sunflower there. There is sunflower there. There is sunflower there, right? And then they used a deep learning method, improved to 15% error, and finally today is 2%. So as of 2017, image classification is better than humans now. So we were beaten by 2017. But something else to remember. 2% error is not 0% error. So if you use this for autonomous vehicle, it will still make errors. Huh? So it's something that policymakers may not fully realize. It is not perfect. Yeah. After 14 million images, still not perfect. What, you want to try 30 million? It's diminishing return. Yeah. Can you get it to 0? I don't know. Yeah. But it's not perfect. Yeah. Neither are humans perfect. They're better than humans, but it itself is not 0%. Keep that in mind as you work with your customers to deliver AI solutions, set expectations. Yeah. Next one, machine translation. The team got together, the world got together, WMT in 17 got together and decided on 2, 4, 6, 7 languages, EU-sponsored. Maybe that's why there are a lot of EU languages there. I picked German because when I brought this out, I realized that they rearranged the sentence a little bit. Yeah? The slow was over there. Has it got better than humans? Yes. for Chinese to English, Microsoft announced last month that they have proven, based on a standard benchmark, that they have exceeded professional translators. I was just in Seoul 2 weeks ago, and there were 2 professional translators at the site. I told them not to worry. Korean is not in there. Right? Yeah. But again, you don't have to worry if you are in there, because these translators are not good at handling context-specific translation. So if you bring it into a company, you have to retrain it. You have to train it a bit more. But this is a huge achievement, becoming better than professional humans in translation. So I downloaded this software, right? I'm going to do in English the Dutch translation using this software in real time. There are a few implications of doing this, right? This is Microsoft Translation. I went to the airport by train and got an earlier flight.
Ik ging naar de luchthaven met de trein en kreeg een vroegere vlucht.
How good was it? It's very good, right? Now, there are 2 things to remember. Firstly, I just downloaded it, did not train it. It just got my voice straight away. Secondly, the delay was pretty short, yeah? And I'm using the cellular network. So it got better than humans. And download the Microsoft Translator. It's a pretty neat one. I've been using it on the way here. I had a French taxi driver, and it worked, yeah? I got here. You say you can only speak French. Okay. Yeah. Professor Hertog mentioned this, games. Right, we know, as Professor said, using knowledge base, IBM Deep Blue beat Kasparov. That's a big number, yeah? Few people know a year before, checkers was won by machine. University of Alberta. And for those in computer science, anyone who did computer science, yeah? Yeah, this was your class exercise, I know, right? The reason the teacher gave you this was because 10 to the power 3, 1,000 combination, the teacher can exhaustively check whether you got it right, yeah? Here we can't, yeah? Right? Here, the number here is we got all the supercomputers and Google data centers of the world, put it together, we still can't solve it in 10 years, yeah? Right? So these are big numbers. So we can only be good enough than humans. We don't perfectly solve the game, no. We just beat humans. Right? Keep that in mind also. Right? Is there a tougher one? Prof said, yes, this is an even bigger number. This is a crazy number. Crazy, crazy big number. Right? So you don't solve Go, you just be good enough to beat humans. And this is where HPE came in and said, is there a tougher one? Right? I was working with Professor Sandholm at CMU for some years, and they said, okay, let's try this one, poker. Yes. Now, it's not as complicated, right? A bit less, but it has one thing more complicated. All these, you know your opponent's pieces. This one, the opponent is hiding the cards from you. You don't know. Moreover, the opponent is constantly trying to deceive you, right? We believe this one is more practical, a lot of practicality in the business world. Like you're negotiating a contract, you don't know what the other party is thinking and what cards the other parties have. So perhaps this can be converted into a business negotiation, a contract negotiation software. So be careful. Next time you see a contract negotiator with an earpiece, yeah? Anyway, yeah, we can. Not between us, yeah, as partners, of course. We'll pull out all our ear sets. Right. Anyway, imagine Professor Sandholm going to the NSF, the National Science Foundation, which is the education ministry. Please give me $3 million. NSF asked why. I want to build a poker machine. Now, we explained it in the contract negotiation way, right? He got the money. So we went to Las Vegas in 2017. There are 4 top poker players we tried. This is the top one. And this is us very innocently sitting here. But there is a network cable connected to a $3 million machine behind. Okay, right. Okay, 2016, we lost $700,000. Yeah, we lost. Okay. So we had to report it to the NSF, right? Yeah. No, it was virtual money. Then we interviewed the 4 top poker players. What was the thing that you spotted that you managed to beat the machine? Almost all 4 said the machine did not bluff very well. Okay, so Professor Sandholm went back and said, okay, came to us, asked for $10 million from the NSF. Yeah, NSF gave the money, right? Built a supercomputer. We built it 10 times more powerful than the one before. Concentrate on bluffing. Came back 2017, won $1.7 million. Right, we won back the $700K and then up $1 million. A few lessons here. One, we interviewed the same top four poker players and asked them, what was it now that is good about the machine? Oh, it bluffed really well. See? 1. 2, you need to spot the weakness of the AI machine. And 3, you need to buy enough compute power to learn fast enough to get to competition again within a year. If we did not get a machine 10 times faster, we can't compete again in 2017. We probably have to compete in 2020, right? And by then, it may become irrelevant, or somebody else would win before us. So these few things tells you the practicalities of AI. It can scale. The learning can scale, but you need to identify what you want to learn or what you want to fix after the initial learning. So it was a good lesson for us. That's Professor Sandholm. He has really got a startup called Strategic Machines. And one of the exciting applications is contract negotiation and auctions, automated auctions, imagine. You can send an auction bot out there, it'll do the best for you. Imagine that, yeah? I close with this video, and let me know what you think, yeah? Oh, never mind. I'll keep going. All right. Oh, there is work to do? Okay, let's pick it up. Not very nice. Not nice. So raise your hands if any one of you felt a little bit bad for the robot. Yeah. This is 2015, right? Imagine how you will feel for the robot in 10 years. Right? On that note, this is an entirely different topic again, called ethics of AI, but that's for another time. Thank you very much. Yeah.